Hello, this video is on acids and bases, specifically the Brønsted-Lowry theory of acids and bases. And so we talked about this in class and learned that if a substance is a Brønsted-Lowry acid, it's a proton donor, and if it's a Brønsted-Lowry base, it's a proton acceptor. And we'll talk about what that means in a little bit to answer some problems. But to do the types of problems we're working on, and just to understand Brønsted-Lowry theory, we need to understand this term conjugate acid-base pairs. So when we have a Brønsted-Lowry acid-base reaction, all that's happening is that a proton is being transferred from an acid to a base. And by doing this, we create conjugate acid-base pairs. And the pairs are only different by a proton. So either it has the H plus or it does not have the H plus. And I use this model in the classroom of Legos or Duplo bricks to talk about the conjugate acid-base pairs. So for example, HNO3 and NO3 minus would be conjugate acid-base pairs because the only thing that's different between them is that one has an H plus and one does not have the H plus. And so those are pairs. And we can see that I'll be using these to represent the anions, and then this block will represent the hydrogen ion that's being transferred from one thing to the other, from the acid to the base. So if we look at one of the example problems that we did in the notes, we'll just go through this and I'll use the Duplo pieces, the Lego pieces, to show you how the how the proton's being transferred. So in the first example, what we're trying to do is label the substances here as either the acid, the base, the conjugate acid, or the conjugate base. And usually the convention in chemistry is to label the things on the left as acid or base and the things on the right as conjugate acid or conjugate base. Okay, so we are starting with, and we're just going to look at the top one first. We're starting with ammonia and water. So here's ammonia, and this will be interesting here. I'm starting with water, which is H2O, which is HOH, right? We know that's water. H plus and OH minus makes H2O. And as we progress the reaction forward, what we end up with is NH4 plus, the ammonium ion, and OH minus. So as we look at our starting materials and then what we end up with, we'll notice that what happened is that this hydrogen ion was moved from the water onto the ammonia. So now we have NH4 plus and OH minus here. So on this side of the arrow, on the left side, these were our starting materials here, ammonia and water, H2O. And as we move to the right, the proton was transferred from water to ammonia, resulting in NH4 plus. So we've added an H plus. So now we have 4 H's and we added the positive charge. Here we got rid of the H plus, so now we're left with OH minus. Okay, so all that's happening is that the proton is being transferred from here to here. That is a Brønsted-Lowry acid-base reaction. Okay, so these are really great, but you might not have these on a test or when you're doing your homework. So the easy way to solve these problems is to first draw a line connecting your acid-base pairs. And it's easy to spot them because the only thing that's different between them is an H plus. So for example, if I'm trying to find the pair for ammonia, NH3, well, this looks really similar, NH4 plus. So I'm going to draw a line. And you have to do this for these problems. It asks you to connect the conjugate acid-base pairs. So I'm going to draw a line connecting those, and then I'm going to draw a line connecting the H2 and the OH, because those look also very similar, and the only difference between them is an H plus. Okay, so I've done that, and then I need to figure out what's going on, what's happening as we go from left to right. And do yourself a favor, always work from left moving right. It will just make more sense if you only move in one direction. It is possible to think of this reaction in both directions, but to keep it simple, we'll go from left to right. And so as we're looking from NH3 to NH4 plus, in order for the ammonia to become ammonium, what had to happen? Did it gain a proton or did it lose a proton to go from NH3 to NH4 plus? Did we lose or gain at H plus? So obviously going from left to right, for here, we gained an H plus, right? In order for NH3 to become NH4 plus, it had to gain a hydrogen ion, okay? And so what that means is that NH3 accepted a proton, right? NH3 accepted a proton to become NH4 plus, and that makes it a base. Okay, so, and we can, if you want to write this, you do not have to, but this gained an H plus, or accepts, okay? And then that means if this is the base, if NH3 is the base, then its pair, its conjugate pair, is the conjugate acid. We automatically know that because we already linked them as conjugate acid-base pairs. Okay? And if we look at the H2O, as we go from H2O to its pair, for H2O to become OH minus, did it gain an H plus or did it lose an H plus to go from here to here? All right, so this time H2O is going to lose an H plus. In order to make H2O look like this, we have to remove an H plus. Right? So in that case, we would say donates H plus or lose, and I think in the notes I put accepts. Either way, accepts or gains, but donates H plus, so that makes H2O an acid. And the reason that we know that these are acids or bases is back to our first definition, right? A base is a proton acceptor, and that's what ammonia did. It accepted, right? So that makes it a base. And a Brønsted-Lowry acid is a proton donor, and that's what H2O is doing, right? It donated an H plus, so that makes an acid. And then we can go to its conjugate pair, and that means that OH minus is the conjugate base. And it's easy to check for this because you have to use them all once. Conjugate pairs should be base and the conjugate acid, or acid and the conjugate base. And on the left side, you'll have an acid and a base, and on the right side, you'll have the conjugate acids and bases. Okay, so if we look at the next one, we'll do this one more quickly. Let's first connect the conjugate acid-base pairs. So we have this thing. It's acetic acid, and it looks very similar to this thing over here, acetate, the acetate ion. The only difference is that the H plus, right? So those two are pairs, and then H2O and H3O plus. The only difference is an H plus. All right, so in order for acetic acid to become acetate, to go from here to here, did it lose an H plus or gain an H plus? All right, this time we had to remove. If we remove this H plus, it becomes that. So that means that this is donating an H plus, which makes it an acid. And watch how quickly you can do this. If you know for sure that this is an acid, you can pretty much fill everything in based on that. If this is an acid, then the thing that it's connected to is the conjugate base, right? Because that's its pair. The other thing must be the base, because you have to have an acid and a base. And then the thing that it's connected to, its pair, is the conjugate acid. All right, I will double check to make sure, but let's see. In order for H2O to become H3O plus, it had to gain an H plus, or accept an H plus, and that is true. According to our definition, a base is a proton acceptor. So here, H2O had to accept an H plus to become H3O plus. And this is kind of an interesting example, just to point out something fun, is that water, depending on the environment, can act as either an acid or a base. So in the top reaction, water was an acid. In the bottom one, water was a base. So we can use the phrase or the term amphoteric to describe a substance like water that can act as either an acid or base. So you really don't know if water is acid or base unless you're given a specific reaction to look at. Okay, so that's how you do these types of problems. Let's really quickly do a couple examples of these that were in the practice for the notes. These are a little bit trickier because you're just given an equation. And so, for example, number 1 says to identify the conjugate bases of the following acids. And so the real key to solving these is to recognize that it's telling you that these are acids. And what are acids? Acids are proton donors, right? So it's telling you that these are going to donate a proton. So what you need to do to write the conjugate base of this is remove an H+. Okay? So if we have H2SO4 and we need to remove an H+, it's only going to have one H now. And we also have to think about the charge. It was neutral, but we just removed an H+, right? An H+ has a positive charge. So we're not only removing the H, we're taking away a positive charge. So that's going to make this now -1 charge. Okay, it went from neutral to -1. All right, so same thing with the next one. If we're starting with OH minus and we know this is an acid, we're being told that this is an acid, we need to remove an H+. So we're going to remove the H, we're left with O, but think about the charge as well. We're removing a positive charge. So it used to be a -1 charge, but we're removing a positive charge. So now it's going to be -2 charge. Okay, it's going to become more negative. So on the other side of that, on this one, number 2, it says to identify the conjugate acids of the following bases. So this time, they're telling you that these are bases. And according to our definition, base is a proton acceptor. So now when we look at these, we need to add an H+ to these. Okay, so starting with HNO3, we're going to add the H. So now it's going to be H2NO3. And we have to add the positive charge. So it went from neutral, it's going to become more positive. So H2NO3+. And then the next one, we already had it over here, but this time it's a base. And bases are proton acceptors. So we're going to add an H here. So if we write this, don't yell at me yet, I'll fix it, don't worry. We're starting as a -1, but we're adding a positive charge. So now it actually becomes neutral. But look, this is not right. OH2, hopefully you recognize that. The answer here is H2O. Okay, don't write OH2. All right, hopefully that helps. Good luck with your homework.